In Section 3, we will discuss adding and subtracting rational expressions with the same denominator and least common denominators. In order to add and subtract rational expressions with common denominators, we basically write the denominator one time and add the numerators or subtract the numerators. Here we have 4p minus 3 over 2p plus 7 plus 3p plus 8 over 2p plus 7. Because we have a common denominator, we are able to write the denominator one time, 2p plus 7, and add across the numerators. So we have 4p minus 3 plus 3p plus 8. Now that we have one fraction, let's combine like terms in the numerator. We have 4p and 3p, which will give us 7p. We have a negative 3 and a positive 8, which will add to make a positive 5, and that's still all over 2p plus 7. Once we get to this point, we see that the numerator can't be factored, neither can the denominator, so we are finished. Where we are subtracting 8y over y minus 2 minus 16 over y minus 2. Again, because we have a common denominator, we can write that one time, and we subtract across the numerators. This becomes 8y minus 16. Now at this point, we see that the numerator, each term has a common factor of 8. So we can factor the 8 from the numerator, and that gives us 8 times y minus 2, all over y minus 2. And because the numerator and denominator have a common factor of y minus 2, we would cancel those and be left with just 8. Example, here we have 3y over y squared plus 3y minus 10 minus 6 over y squared plus 3y minus 10. Again, we have one common denominator, y squared plus 3y minus 10. So we write that once. We subtract across the numerator, 3y minus 6. And in this example, it appears that we can factor the numerator and denominator. In the numerator, we have a GCF of 3. That gives us 3 times y minus 2. In the denominator, we have a trinomial. We have no greatest common factor. The coefficient of our squared term is 1. So we can break that down into two binomials. The first term of each will be y, so because y times y is y squared. Now we look at the constant term at the end. We want two numbers that will multiply to negative 10, but add to a positive 3. And as you go through the list of factors for 10, you would find it would be 5 times negative 2 gives us negative 10, and 5 plus negative 2 equals positive 3. So we fill those in, fill in the gaps with a positive 5 and a negative 2. Now we cancel the like factors in the numerator and denominator, and we're left with 3 over y plus 5. Example, here we have 3x squared plus 8x over x minus 6 minus 25x plus 6 over x minus 6. Remember, when we are subtracting a polynomial, as we are with the 25x plus 6, we must distribute that negative sign to both pieces that follow it. Once we do that, because we have common denominators, we write the denominator one time and write the subtracted polynomials in the numerator. 3x squared plus 8x minus 25x minus 6. Now we combine like terms in the numerator to give us 3x squared minus 17x minus 6 all over x minus 6. Now we can see that the denominator won't factor, but the numerator might. So let's off to the side, write the numerator, and try to factor it into two binomials. We have 3x squared minus 17x minus 6. We have no greatest common factor, so we go straight into the factor by grouping method. We multiply the first coefficient and the last coefficient. That gives us negative 18. So we are looking for two numbers that will multiply to negative 18, but add to negative 17. And so just like we would have done in Module 9 or Module 6, we look for all the possible factors, and the factors that will satisfy both conditions are positive 1 and negative 18. Positive 1 times negative 18 gives us negative 18 when we multiply. Positive 1 plus negative 18 equals negative 17. So we will take these two factors and put them in place of the middle term in our trinomial. When we do so, that gives us 3x squared plus x minus 18x minus 6. We group the first two terms, group the last two terms. The GCF of the first group is x, so it gives us x times 3x plus 1. In the second group, the GCF is 6, and they're also both negative, so we factor a negative 6, and that leaves us with 3x plus 1. Now we have a common binomial. We factor out the 3x plus 1, and it leaves us with x minus 6. So what we were able to do is rewrite the trinomial in the numerator as 3x plus 1 times x minus 6, all divided by x minus 6. So we can see that we have a common factor of x minus 6 in the numerator and denominator. We cancel those, and the final answer will be 3x plus 1. Subtract rational expressions with different denominators, we have to change them to equivalent forms that have the same denominator. Now, that involves finding the least common denominator of the two original rational expressions. To find the least common denominator, first we factor each denominator completely. In step 2, the least common denominator is the product of all unique factors found in step 1, each raised to a power equal to the greatest number of times that the factor appears in any one factored denominator. So let's try to put that into practice. We want to find the LCD of the following rational expressions. We have 6y, and we have 4y plus 12. Starting off, we want to factor each denominator. 6y can factor into 2 times 3 times y, so we write the prime factorization of the coefficient as well as the expanded form of the variable. 4y plus 12, first of all, has a greatest common factor of 4, so we write 4 times y plus 3, and we know that we can rewrite 4 as 2 times 2, so 2 times 2 times y plus 3. So when we look at our unique factors that show up in each prime factorization, we have 2's, we have 3's, we have a factor of y, we also have a y plus 3. And we need that to show up the greatest number of times from each list. So let's start with the 2's. In the first list, we have 1 2. In the second list, we have 2 2's. So the greatest number of times we ever see 2 is in the second list. So we will keep these. We don't care about the least number. So 2 times 2, let's off to the side write the LCD. We'll start with 2 times 2. Now that we're finished with the 2's, let's look at 3's. We have 1 factor of 3 in the first list. We don't have any factors of 3 in the second list. The 3 that is attached to the y does not count. So the most that we ever see 3 is 1 time, and that's in the first list. So we multiply that factor in the least common denominator. We now look at our factor of y. We have a factor of y that shows up once in the first list. We don't have any plain factors of y in the second list. So the most we ever see a factor of y is once. So we multiply 1 factor of y. And then finally, we have the factor of y plus 3. We don't have any y plus 3's in the first factorization. We have 1 factor of y plus 3 in the second factorization. So we include 1 factor of y plus 3 in the least common denominator. Multiplying all of these factors together, 2 times 2 times 3 is 12. So this becomes 12y parentheses y plus 3. And we would leave it just like this. We want to find the LCD of the following rational expressions. Again, when we say least common denominator, we are only concerned with the denominators on each term. So we start by writing the factorizations of each denominator. Now hopefully you are very proficient at factoring by now, or you're able to do this on your own. X squared plus 4x plus 3, once you take the time to factor, you will get x plus 3 times x plus 1. We then go to the second fraction, x squared plus 10x plus 21. We're looking for two numbers that multiply to 21 but add to 10, which would be 7 and 3. So x plus 3 and x plus 7. So when we talk about the unique factors from each list, we have x plus 1's, we have x plus 3's, and we have x plus 7's. We're looking for the most times each unique factor shows up in each factorization. So let's start with x plus 1. In the first factorization, we have one factor of x plus 1. In the second factorization, we don't have any, so the most it ever shows up is one time. So in our least common denominator product, it will show up one time. We now go to our x plus 3 factors. We have one factor in the first factorization. We also have one factor in the second factorization. So the most it ever shows up is one time. So we write one factor of x plus 3 in the least common denominator product. Now we look at the x plus 7 factors. The first factorization contains 0 x plus 7 factors. The second factorization contains 1, so the most the x plus 7s ever show up is one time. So we will also have one factor of x plus 7. And we will actually leave it in this form. We do not want to try to FOIL or do anything crazy. Just leave it with your parentheses and your factors beside one another. We have 5x squared minus 5 and x squared minus 2x plus 1. We're trying to find the common denominator between these two expressions. Let's start by factoring 5x squared minus 5. And this will be a two-step process. First, we see we have a GCF of 5, so we factor out the GCF. We have 5 times x squared minus 1. Remember, 1 is the same thing as 1 squared, so we have x squared minus 1 squared, and that's in the form of a difference of squares. And difference of squares factors into x plus 1, in this case, and x minus 1. Let's try the same thing with the second denominator, x squared minus 2x plus 1. We're looking for two numbers that will multiply to a positive 1, but that will add to a negative 2. That would be negative 1 and negative 1. So we'd write this as x minus 1 times x minus 1. So now we have our two factorizations. And in those factorizations, the unique factors are 5, x plus 1, and x minus 1. Let's look and see where it shows up the most times in each factorization. So we start with 5. We have one factor of 5 in the first factorization, 0 factors of 5 in the second factorization, so the most we ever see it is once. We write one factor for our answer. We then go to x plus 1. We have one factor of x plus 1 in the first factorization. We don't have any factors of x plus 1 in the second factorization, so the most we ever see the factor x plus 1 is one time. We write one of those. Minus 1. The first factorization, we have one factor of x minus 1. In the second factorization, we have two factors of x minus 1. So the most that x minus 1 ever shows up is 2 times. So we need two factors in the answer. We write x minus 1 times x minus 1, or we could write x minus 1 squared. So the LCD would equal 5 times x plus 1 times x minus 1 squared, and it would be perfectly fine if you wanted to write that out as x minus 1 times x minus 1. Again, we want to find the least common denominator of these two rational expressions. So we look at the denominators. We have x minus 3 and 3 minus x. So we try to factor these as far as we can. X minus 3 doesn't factor. And so just like with prime numbers, it is its own factorization. We could write it in parentheses if we wanted to so that we realize that's one factor. 3 minus x, if you remember the trick that we used before, when our terms only differed by a negative sign, we could factor out the negative 1 and reverse the order. Discussing least common denominators. We are not concerned with a negative, because a negative in the denominator could simply move to the numerator, and then we would ignore it. And so here, the least common denominator, we have an x minus 3 factor in the first factorization. We have an x minus 3 factor in the second factorization. They're exactly the same. The least common denominator will just be x minus 3. Writing equivalent rational expressions. Because when we have different denominators, we will need to change rational expressions into equivalent forms. We will use the principle that multiplying by 1 will give you an equivalent expression. And that means we need to multiply the numerator and denominator by the same factor. Examples, we want to rewrite the rational expression as an equivalent rational expression with a given denominator. So we start with 3 over 9y to the 5th, and we want a new fraction where the denominator is 72y to the 9th. Now, one way to do this, and there are multiple ways, but one way to do this is to divide the new denominator by the original denominator. So going from right to left, we're going to divide. And once we find that quotient, we're going to multiply in the numerator. And that will give us the new numerator for our fraction. So let's try this. We take 72 y to the 9th divided by 9y to the 5th. This out, we would need to write the prime factorization of the numerator and the denominator. Remember, you can do that with a factor tree. I'm not going to write the factor tree for these problems. You can always do that, pause the video, and then come back once you have your prime factorizations. So as we go, 72 is 2 times 36, which is 2 times 18, which is 2 times 9, which is 3 times 3. Y to the 9th, I'm just going to leave that as y to the 9th. And we will use exponent rules in order to simplify these exponents. 9 is 3 times 3. We'll leave that variable as y to the 5th. Now, when canceling common factors with our numerical coefficients, we have common factor of 3 and another common factor of 3. So the numerical coefficient, we're left with 2 times 2 times 2 in the numerator. The variables, remember when we are dividing variables, we subtract the exponents. So we're left with y to the 9 minus 5, or y to the 4th. So when we divide, we get 8y to the 4th. But we want to divide and get 8y to the 4th, and we multiply the numerator by what we just found. So 3 times 8y to the 4th would give us 24y to the 4th. So the new fraction would become 24y to the 4th over 72y to the 9th. Another example. We have x over x cubed plus 10x squared plus 21x equals, we're trying to find a new numerator for a new denominator, x times x plus 6 times x plus 3 times x plus 7. We're going to go through the same process. We're going to go right to left, we want to divide. Then once we find our expression, left to right on top, we're going to multiply. In this example, it will be easier if we start by factoring the first denominator before we set up our division. And so we can look and we have a GCF of x. We factor in x, and that gives us x squared plus 10x plus 21. As we continue to factor, this will factor into x plus 3 times x plus 7. So we have x times x plus 3 times x plus 7. Now let's set up our division and continue from there. We have the new denominator, x times x plus 6 times x plus 3 times x plus 7, all divided by x times x plus 3 times x plus 7. Now we can cancel common factors. We have a common factor of x plus 7, of x plus 3, and of x, and we're only left with x plus 6. So in the numerator, we will multiply by x plus 6. That will just give us x times x plus 6. So now we have a new numerator and a new fraction.